Okay. Neyse ben kayda başlayayım. Olmazsa diğer arkadaşlarımız kayıttan izlerler. Nasılsınız efendim?
İyiyiz hocam, teşekkürler. Siz nasılsınız?
Vallahi fena değil. Covid olacağım günü bekliyorum. Bu gidişte hepimiz olacağız galiba.
Evet, öyle gözüküyor maalesef.
Yani paralel şubedeki 2 hoca ki çok dikkatlidirler. Bülent Hoca ile Bora Hoca oldu geçen hafta. Bilemiyorum valla. Kampüste ben pazar günü gittim kampüse boş diye. Kampüste de müthiş dedikodular vardı. Şeydin bu yukarıdan aşağı inen yol var ya ana kapıdan. Onun diğer tarafında herkes Covid'liymiş diye. Artık gülsem mi ağlasam mı bilemedim. Bayağı sıkıntılıydı. Okay guys. Now we are delayed a bit, but I think there are some connection problems and yeah, we're already some 27 minutes late. So I think I will start with a short video. So that will sort of recap the stuff we did last week. And hopefully, Egiz is also here. Nice, nice. Okay, at least there are 4 students. Now I will start with the video so that we remember what I already tried to talk about last week. And let's see, it's a short one. I have 3 or 4 short videos. This is about 5 minutes, I think. No, 7 minutes it was. Okay, let's start. All right, I think, and I hope you can see it now, but somehow there is a little problem. Wait a second. Okay. All right, here we go. Here we start.
Hi, I'm James, the Bald Engineer. Both of these are transistors. One is a BJT and the other is a MOSFET. Can you tell the difference? If not, that's okay, because in this Adams video, we're going to take a look at MOSFETs, how they work, and how you can use them in your circuits. So let's get going. This video is part of a 2-part series on transistors. The previous one covered bipolar junction transistors, BJTs, while this video covers metal oxide semiconductor field effect transistors, known as MOSFETs. Generally, you'll use a BJT for small loads, say less than 1 amp of current, while MOSFETs are well suited for applications with much higher current. For the video on BJTs, see atoms.com/EP10. For now, let's move on to MOSFETs. Moss is a flowerless plant that typically grows 1 to 10 centimeters. Some mosses grow up to 50 centimeters and can be commonly found on trees. Wait a minute. This is the wrong script. Hold on. The tree sounds right. Okay, here's the other stuff. Okay, let's try this again. MOSFETs belong to a family tree of field effect transistors, or known as FETs. There are JFETs, MOSFETs, and IGBTs. JFETs actually work a little bit like a BJT, which we've already talked about. For this video, we're focused on the MOSFET, which has 2 types of modes called depletion and enhancement. A depletion mode MOSFET works like a normally closed switch. Current can flow when no voltage is applied. Applying a negative voltage actually causes the current flow to stop. An enhancement mode FET works like a variable resistor. They come in N-channel and P-channel types. Enhancement mode FETs are by far the most common transistor used today, so let's focus in on them. Here's the symbol for an N-channel enhancement mode MOSFET. And here's a TO220 style transistor. The pins of a MOSFET are identified as the gate, the drain, and the source. The field effect part of their name suggests they work by voltage, compared to a BJT, which works by current. When voltage is applied between the gate and the source, current is allowed to flow between the drain and the source. Here's the really cool thing about MOSFETs. They are variable resistors controlled by voltage, which means depending on the voltage applied between the gate and source, the resistance between the drain and source will vary. With a low voltage at the gate, the resistance from the drain to source is very high. It's kind of like an open switch. As we increase the voltage at the gate, we pass a threshold voltage, and then the resistance from the drain to the source drops, and it drops very quickly. The key difference between a MOSFET and a BJT is that the output current isn't a multiplier of the input, because MOSFETs are all about voltage. Since the resistance is between the drain and source, it is known as RDS on, and can always be found in the MOSFET's datasheet. For example, this is a FQP30N06L. Let's take a look at its datasheet from Fairchild. We can see that RDS is given when there are two different voltages from gate to source. At 10 volts, the on resistance will be about 27 milliohms. And while at 5 volts, the on resistance is only about 35 milliohms. That's pretty small when you think about it. We picked this MOSFET on purpose. It is known as a logic level MOSFET because the voltage from gate to source, VGS, is lower than 5 volts. In other words, the threshold to turn the MOSFET on is low enough to be used by an Arduino or Raspberry Pi. Not all MOSFETs are logic level compatible, so it is very important to check to see what the VGS threshold is before using it in your circuit. Since you will probably use a MOSFET in high current applications, it is important to check how hot it is going to get. Here's how we calculate if we need a heatsink or not. The formula to determine how much power the MOSFET dissipates is resistance times current squared. In this case, the resistance is RDS on, and the current is whatever your load will draw. Let's use an example of a motor that draws 1 amp of current. This means we multiply 35 milliohms by 1 amp squared to get 35 milliwatts. Okay, now we need a few more things from the datasheet. First, we need the junction to ambient coefficient, which is R theta JA, and in this case is 62.5 degrees C per watt. We also need the maximum junction temperature, which in this case is 175 degrees C. Using this formula, we can calculate the maximum power the transistor can dissipate without using a heatsink. We take the maximum junction temperature minus the ambient temperature, which is going to be 25 degrees C, and divide by the thermal resistance. This gives a maximum dissipation of 2.4 watts. In our example, we are only dissipating 35 milliwatts, so we're safe to operate without a heatsink. Now, you might be wondering, how can the number we calculate be 2.4 watts when the datasheet clearly said 79 watts? And that's a really great point. The 79 watts is if we had the ability to cool the transistor's case to 25 degrees C, which means you have to be using some kind of heatsink. But we're going to cover more on that in a later video. Let's review what you need to know to use a MOSFET as a switch. Number 1, find out which pin is the gate, drain, and source. Number 2, look at the datasheet to determine the threshold voltage, which is going to be shown as VGS or VTH. Find the drain to source resistance or RDS on. Number 4, look at R theta JA and the maximum junction temperature to calculate how hot the MOSFET will get. Visit adohms.com/MOSFET-guide, all lowercase, to download a simple PDF form you can use to calculate these parameters. MOSFETs are cool little devices, but they're also a little bit complex, so we'll cover them in more detail in future videos. Make sure you follow us or subscribe to know when new video tutorials are released.
All right, guys. Now that was a short, quite a short video. And now the majority of you are computer engineering students. I would like to show you another video. And let me see, how many are you? Oh, you're only 4. All right. Now I'm going to show you another video, and you probably want to know the link to this video. The first link, I'm giving it to you. And now the link to the second video, it's right here. And it's coming. Okay. Now let's watch the second video too. And in the meanwhile, hopefully more students can join us. Here we go.
At the core of every computer are devices that actually perform the computations. In most modern computers, we either use NMOS and PMOS transistors as the base of most of our operations. And in this lecture, we'll be focusing on how we use these two transistors to create logic gates. Now, this is the NMOS transistor itself inside this circle, and we have some conventions of how we use it. So we connect this lower terminal, terminal 2, to ground. It's sufficient just so you know that this is the convention, and you can explore why in future courses. And then we have a gate, which is our inputs, and that's how we control the transistor from our perspective, and that'll be a 0 or a 1. And then this terminal 1 connects to other gates or the output of our logic gate. And then we've got our PMOS transistor over here, which behaves in an opposite fashion. We have our transistor here, and notice this little symbol that tells us this is the PMOS transistor. And we connect terminal 1 here to this high voltage VDD, which is usually like about 1 volt, but that's going to be varied based on the technology. And then we have our input gate, which allows us to control this transistor. And then terminal 2 connects out to other circuits or other logic gates. And so how do we actually make these work, and what do these actually do? And so basically a transistor is a electrically controlled switch. If we put a 1 in, or a high voltage, the NMOS becomes a closed circuit, whereas the PMOS becomes an open circuit. And if we were to switch, well, let's explore this a second longer. So when this is closed or shorted, there's a direct path from ground up to here. So basically our output terminal has a 0 volt output. Whereas this guy, since there's an open circuit, there's no current or anything going through this. And so this is just basically a dangling wire. There's nothing there. It's not connected to anything. However, if we switch our inputs, the entire behavior changes. Our NMOS becomes an open, and our PMOS becomes a short. And so now there's a direct path between our output and VDD. So now this is going to be our high voltage VDD. And we can keep altering these behaviors. We can alternate them between 0 and 1s. And because they have opposite functionality, we call them complementary. And complementary MOS or CMOS is how we talk about NMOS and PMOS as a group, and any other type of logic that has a similar functionality. The amazing thing is that we can use just a PMOS and an NMOS transistors to create any circuit. And so here we have a NOT gate, and we'll show you how this works. If we have an input of 0, our P-type is going to become a short and directly connect the output to VDD. So when our input is 0 volts, our output is going to have VDD volts, which is a logical 1. On the other hand, this N-type is going to be open, so there's no connection between our output and ground. if we input a 1 or VDD volts, we have a direct path between ground and the output. So our output is going to have 0 volts and be a logical 0. And our p-type is going to become an open, so there's no connection between VDD and the output. And so this is how we build our NOT gate, which has this symbol. When we build more complicated or complex digital logic circuits, it becomes important to notice there's another part of what makes these guys complementary. So down here, NMOS transistors are connected in series. That means the output of one is connected to the terminal of the other. Whereas our PMOS up here are connected in parallel, where both of their outputs are connected together, and they're both connected on their terminals to VDD. And these differing paths, this parallel path versus series path, is really important. That anytime you have a PMOS in parallel, you need to have an NMOS in series. If you have a PMOS in series, you need to have an NMOS in parallel. And that's how we build our logic gates, so that we maintain this complementary functionality. Now let's look at what this circuit actually does. So let's input A is 0, B is 0. So when A is 0, this PMOS is going to be a short, and when B is 0, this PMOS is going to be a short as well. And so both of these connect our output directly to VDD. So our output should be a 1. And down here, our A is connected to our NMOS, so that's going to become an open. And B is going to be connected to this NMOS and create an open. So there's no path between ground and the output. So indeed, our output is 1. And let's try another input combination. So let's try with 0, 1. And when A is 0, we're going to have a short on this PMOS, just like before. And with B is 1, this is going to create an open on this PMOS. A with 0 is going to create an open on this NMOS, and B with a 1 is going to create a short. So here, our ground is still cut off from the output, but we do have a direct path from VDD down to the output, so our output's going to be 1. Now let's try the next combination, 1, 0. This is going to be exactly like before, except a little bit flipped. So A is going to result in this being open. This B is going to cause this to be short. And then this A is going to cause this NMOS to be shorted. And this B with 0 is going to cause this NMOS to be open. So again, there's no path between ground and the output, but there will be a path between VDD and the output, so the output is 1. All right, one last combination to go. We got A is 1, B is 1. That means A is going to be an open on this PMOS, B is going to be an open on this PMOS, and then A is going to result in a short on this NMOS, and B is going to result in a short on this NMOS. So now we have a path between ground and the output. So our output is 0, and we have no paths between VDD and the output. So that reinforces that this is a 0. If you recognize this truth table, you should recognize that this is the NAND function, the not and, which has the following circuit symbol. We can now use this NAND gate that we constructed to create an AND gate if we just concatenate this not afterwards. So we've got our NAND, and this is our not, and this would result in A, B as our inputs, C as our outputs for an AND gate. This is one reason why we tend to use only NAND gates in our implementation of actual computers, because an AND gate is a lot more complicated. But anyways, we'll find out more about that in future lectures as well. So let's look at one last circuit, and I'll just give the punchline away for this one. This is a NOR gate, and we'll see exactly how this behaves. But I want to draw attention back to the series versus parallel. Here, our PMOS are in series, whereas our NMOS down on the bottom here are in parallel because they share that common point over here. And so that should hopefully reinforce the idea that we always do things complementarily between PMOS and NMOS. So let's look at the inputs. When A is 0, B is 0. A creates a short on the PMOS, B creates a short on this PMOS. And then the A comes around here and creates an open on the NMOS, and B creates an open on this NMOS. So we have a direct connection between VDD and the output, and no path between ground and the output. So output is 1. Let's try the next symbol combination with 0, 1. 0 creates a short here and an open here. So there's no path between VDD and the output. And then we've got 0 over here, so this guy becomes an open, but the B being 1 here creates a short for this NMOS, so we have a path directly from ground to the output, so that creates a 0 output. Next input combination, 1, 0, B is 1, so we have a open here and a short on this PMOS because of the B, and then this guy is going to be open and this guy will be shorted. So now we have a different path, but we still have a path nonetheless from ground to the output, so our output will be 0. And then when we put both of these as 1, both of our PMOSs will be open and both of our NMOSs will be shorted, so we have 2 paths from ground to the output, so C will be 0 and our output will be 0. And this again creates our NOR gate, which has the circuit symbol NOR. And we can combine NOR with NOT to create OR. And just like our NAND, we generally will prefer to use NOR gates exclusively in our designs rather than using AND, ORs, and NOTs.
Okay.
Netflix'te vizyona giren Don't Look Up, Yukarı Bakma filmi çok ses getirdi.
Okay, I'm sorry, guys. I'm really sorry. It did it by accident. Okay, now in the meanwhile, we are 6 plus me and Berk. I am hoping that the others don't have any real troubles connecting. Now, let's go back to the PowerPoint slides. And here we are, our last 2 weeks, and it's going to be over in about 10 days. The semester is going to be over in about 10 days, and then we'll have our final on the 28th of January. Let's see. First, a recap of transistors, either bipolar junction transistor, and again, I'm repeating bipolar because its operation involves conduction by 2 charge carriers. Junction because there are 2 junctions on the path of conduction. One is forward bias, that's the base emitter. The other one is reverse bias, that's dust collector base. And it was invented by Shockley, Brattain, and Bardeen, which brought them the Nobel Prize in 1956. When we move over to field effect transistors, they are unipolar. The operation involves only one kind of charge carrier, either electrons or holes. So that's basically the majority carriers. And therefore they have less noise. An electrical field is created by application of voltage, and that controls the current. And it was shown in 1957 that the metal oxide semiconductor could be created. And 11 years later, IBM has effectively realized the idea experimentally. When we come to the principles, we have a base which is connected to the source. The substrate is here. If the substrate is of p-type, that's NMOS. If the substrate is of n-type, it's PMOS. And it's totally symmetrical. The pins are source, gate, and drain. And there are 2 regions that are heavily doped. These are the source region and the drain region, but they are separated from each other And this separated area becomes the channel over which the conduction of current is possible when this channel, which is of p-type, is converted to n-type by application of a VGS. And depending on what type of channel we're creating, we either have a positive or a negative VGS. And so a positive voltage is applied to the gate to create an n-type enhancement channel here. And since the source is grounded, the gate voltage appears between gate and source. And it basically, the positive voltage to the gate causes the holes between these two regions to be pushed towards the base, and it pulls the electrons from the base or body, and this way creates a channel. And there is a threshold when a sufficient number of electrons accumulate near the surface, then the source and drain regions are connected. The operation modes were three. One, cutoff, and there is no drain current. Of course, there is never a gate current. And this, the cutoff region, is when VGS is less than VT. That means no channel is created. Then we have the triode region, where the MOS behaves like a resistor. And that's when VDS is less than the over voltage, or VDS is less than the saturation voltage. And the drain current is a function of VDS. But once we get into the saturation region, the drain current is only a function of VGS and VTH, and these are constant once VGS is larger than the threshold voltage, and VDS is equal or larger than VGS minus VTH. So the output characteristic has a family of curves, and these are parallel in ideally, and that means there is no early effect. And if there's any early effect, these have a slight slope, but they're still a family of output currents or drain currents as a function of the applied VGS. And in the saturation region, the channel looks like this. So it's larger or deeper on the source end, much shallower on the drain end. And the reason for this is, of course, the positive voltage between the drain and the source. So that's a summary of regions of operation. And this is the transfer curve. We have no input characteristic because there is no input current going into the gate here. Now, we did biasing of MOS last week, and now I want to show you the small signal equivalent pi circuit. And since there is no gate current, the gate pin is unconnected. Between the source and the drain, we have a voltage dependent current source. And if there is an early voltage, we have an output resistance. These two come in parallel. So this dependent source can actually be represented as a GM, transconductance, times VGS, the input voltage, right? And so what is GM? GM is the square root of 2 mu NC ox, W divided by L, that's the important parameter of the transistor, and drain current. So like the small RE in BJT, GM is also dependent on the biasing parameters, and in fact, drain current. So what are the possible topologies? You remember in BJT, we had common emitter. Analogous to this one, we have a common source. In BJT, we had a common base. The analogous one is common gate. In BJT, we had common collector. Analogous to this, we have common drain or source follower. In BJT, this would have been called also emitter follower. So how do they look? The common source has the input from the gate, output from the drain. The common gate has the input from the source, output from the drain. The common drain has the input from the gate, output from the source. So they look very, very similar to BJT circuits. In fact, you'll see when we go over input, output resistances and gain calculations, they are very, very similar. Now, first off, let's discuss the common source, right? So analogous topology was common emitter. This is the small signal circuit, R pi, GMV pi, and R0. And of course, R0 is a function of the early voltage. If the early voltage is very large, this disappears. And you remember we had base dividing resistors, and at AC, they come together in parallel. And the emitter can be with a resistor, without a resistor, or with a DC resistor for biasing purposes. But if we use like a bridging capacitor at AC, the emitter is directly connected to the ground. So what is the input resistance here? It's the parallel equivalent of these base dividing resistors times the R pi. And the output resistance is RC in parallel to R0. But if R0 is negligible, output resistance is RC. So, and what is the gain? Well, if you remember it, the gain was a function of RE. This is HFE RE. RE, RC, and whatever is connected to the emitter at AC. So that means here, the gain will be a function of RC parallel RL, RE plus RE. So that was our analysis earlier. So now do this with the MOS. This is the MOS at DC. So basically the DC circuit looks like this. And we do all the biasing calculations on the circuit. But at AC, of course, the VDD is going to be 0. So RD will come in parallel to RL. RG1 will come in parallel to RG2. And R6, so the internal resistance of the source, will be connected directly to the gate. All right, the source, since it's bridged, it's going to be connected to ground. All right. And the input voltage or the voltage between the gate and the source or ground is basically VGS. What else? Let's put the equivalent circuit in here. So let's go back. So these will come in parallel. RD will come in parallel with RL. All right. That's what it is. They come in parallel, and here we have VGS. The source is grounded, so VGS is the input voltage. This is GM-VGS. If we need to take care of R0 is early voltage divided by ID. So what is the input resistance? Obviously, since there is an infinite input resistance here, it's the parallel equivalent of these two gate dividing resistors. And so their parallel equivalent is important because our sig, so the internal resistance of the source, and the parallel equivalent, the signal is basically voltage divided on these resistors and by this factor. Anyway, VGS is VI. Let's go to the output side. Output resistance is RD in parallel to R0, or if there is no R0, it's basically RD. So that means whatever current is here, that dependent source, these three resistors are going to come parallel, and the output voltage is the parallel equivalent of these three or two multiplied by the dependent current source. But since the current goes upwards, we will have a minus sign. So the output is minus GM VGS RD parallel RL R0, and the gain will be V0 divided by VGS. So it's basically minus GM RD parallel RL parallel R0. And that is pretty much the formula, very similar to the formula we had for common emitter circuit. And GN, again, to remind you, is expressed by the square root of this. Okay, so the total gain is then minus Rin divided by Rin plus R sig, GM, and the parallel equivalent of these three. Now, let's move over to common collector topology in BJT. Remember it. So, from the base, the output is taken from the emitter. And we have an emitter resistance. Of course, we need to have an emitter resistance and a load resistance. And this is the parallel equivalent of base dividing resistors. So how did we analyze this? For simplicity reasons, I use a T equivalent BJT small signal circuit. And so here the input is to the base, and we have the alpha I dependent current source connects to the collector, and collector VCC in AC terms is connected to ground. On the other hand, in base and the emitter, we have the small RE, which was the thermal voltage divided by the collector current, and then the capital RE. So if R0 is neglected, RE comes in parallel with RL, and they come in series with RE. If R0 cannot be neglected, then R0, RE, and RL, they all come in parallel. So the voltage, output voltage, is then that current I multiplied with the parallel equivalent of all these resistors connected to the emitter. So input resistance is found from the parallel equivalent of these three plus RE multiplied by the current divided by the current. So the input resistance is a very high resistance. So the total input resistance Rin is then the base dividing resistors in parallel with that RIB. On the other hand, output resistance, I don't have to go through this, you remember this, was the parallel equivalent of R0, RE, then that small RE plus whatever is connected to the base divided by beta plus 1 or HFE plus 1. So whatever is connected to the base is R sig in parallel with RB. Since the parallel equivalent of all these three are smaller than the smallest, and the smallest is this one, the output resistance is very, very small. And the gain is very close to 1, but smaller than 1. And it was equal to whatever comes to the emitter divided by small re plus whatever comes to the emitter multiplied by the voltage dividing function of these two resistors, R in and R sig. So analogous common drain topology. Input is applied into the gate, output is from the source. So if there is no resistor, a source resistor, then we basically have the load resistance connected to the source. And the T equivalent small signal circuit consists of 1 over GM and GM VGS. So what is the output voltage? Output voltage is RL times the dependent source, GM VGS. And what is VGS? VGS is basically the voltage between these two. The input resistance is, of course, infinite because there are no voltage dividing resistors, because there is no current going into the gate. So basically, VG is V sig because no current flows here. That brings the gain to the input voltage is the voltage appearing here. So it should be this series resistance here multiplied by the current divided by whatever is at the output or whatever is at the output. So RL divided RL plus 1 over GM. So instead of RE, we have 1 over GM right now. So that's the analogy. Do you see it? And so at this point, I think we need to have a little break. And so I will stop sharing for a moment. How many are we? We are still 4. Oh my goodness. Oh my goodness. I guess the others could not connect. So let's have a 15-minute break and then we'll continue. Okay? Okay, everyone? All right, good. All right. Evet efendim. Toplam kaç kişiyiz? 6 mı? Oh my goodness. We are only 4 students. All right. All right. So we'll continue and hopefully the others will join us. It's sort of really difficult to go through these times again, I just learned during the break that in North America, they went to full online lectures in the lower grades. That means middle school, elementary school, and they were discussing what they should do with the universities. So apparently we are going to some sort of a lockdown again. Well, apparently this is it. Anyway, I would like to show you, remind you of current sources and show you another video. Hopefully the video is this. Hopefully we won't have a power cut. So here we have current sources, and we'll start with the BJT. It's a short video, and then go over to the most current sources, that is mirrors.
Today we will be talking about the current source circuit, how they work and how they are useful in a multitude of electrical circuits. We will explain these concepts using real-world analogies. Normally, to control current in a circuit, a resistor will be used, and they will act according to Ohm's law, which relates current to voltage divided by resistance. However, resistors are difficult to implement on ICs and are sometimes impossible to manufacture due to the size constraints. So we use current mirrors and current sources to properly bias amplifiers on an integrated circuit. A current mirror, as the name suggests, mirrors the current flowing in the left channel onto the right channel. The current on the left side to be mirrored is called the reference current. But before we get into the details of how a current mirror source actually works, we need to know how a transistor works. As we've seen before with the famous water analogy, the bipolar junction transistor can be modeled with the following diagram. Imagine that the flow of water is the electrical current. As the water flows into the valve, it pushes up against the plug, allowing the larger flow of water to commence from the top. This effectively acts as an amplifier, since we are creating a large amount of current from a relatively small source. Note how a little bit of flow from the input joins the larger stream of water. This is very similar to how a real bipolar junction transistor works. The base current is added to the collector current, which is then outputted through the emitter. When we put two identical BJTs in the following configuration, by connecting the bases together, we create a simple current mirror. When a DC current is applied to the left transistor's collector, it becomes the reference current. Watch what happens to the current on the right transistor. A little bit of current flows to the base connection, and since we have identical transistors, the current is equally divided and injected into the bases. So the reference transistor turns on and lets some current pass through. Remember that the sum of twice the base current and the collector current is equal to the reference current that we want mirrored. The base current acting on the second transistor allows an almost equal amount of current to flow through it. This is how the current is mirrored. Through this process, we can replicate the reference current at various points in the circuit. This is known as current steering.
We now consider the basic MOSFET current mirror, which follows the same principles of the BJT current mirror, but uses two field effect transistors instead. Voltage is analogous to water pressure in our example, so we have a pressure-activated water valve to serve as a model. At the reference transistor, the drain current is equivalent to the reference current because a field effect transistor does not draw any current through its gate. This means that the output current of a MOS current source will be closer to the reference current than a circuit that implements BJTs with a finite beta. Both of the FETs are operating in saturation mode. This means that there is a constant potential applied across them. The drain current of a MOSFET is a function of both gate source voltage and the gate drain voltage. Of course, for a current mirror to function, it needs a reference current. This is set by attaching an appropriate size resistor to the collector or drain of the reference transistor. As we mentioned at the beginning, current mirrors are essential in integrated circuit design when a constant current is required regardless of voltage. We also see the circuit heavily utilized as a constant load in differential pair amplifiers. There are many variations of current source circuits that optimize the behavior for certain applications, but we have seen the most basic designs and how they function.
Okay. Stop share. So hopefully we remember the BGT current sources, and we see in this video how a current source can be implemented using the MOS. Now let's go back to the slides. And we had common collector and common emitter designs and their analogous topologies as common drain and common source. Now we come to the common gate, right? So the BGT common base topology looked like this. The base is either connected to the ground directly or over a resistor. The input is applied into the to the emitter. The output is from the collector. Pretty much things that you saw before the second midterm. And let's see. The small signal circuit looks like this, again, with the T equivalent small signal circuit. We have the RE and alpha IE, and the large RE is connected from the emitter to the ground. The signal comes into the emitter. So what is the input resistance? Input resistance is basically the RE comes in parallel with that RE. So it's the parallel equivalent of these two. Since small RE is very small, the input resistance is smaller than the small RE. So again, small. The output resistance is again RC if the early voltage can be assumed infinite. So what is the output voltage then? The output voltage is whatever current flows over these two resistors, but since the current flows upwards with a minus sign, so minus alpha IE are seen in parallel to RL. Okay. What is the input voltage or signal voltage? Well, the signal source has its own internal resistance, and that comes, or actually that voltage divides with the input resistance, the voltage, and that voltage appears at the emitter. So this takes care of that part. Then we have the voltage over here, alpha IE are seen parallel to RL. That's this part. Where does the RE come into play? Well, the gain is output divided by the input, right? All right. The input voltage, VE here, is basically that current times RE. So output is alpha IE RC in parallel to RL. Input is basically RE minus VI RE. So the total gain can then be represented by this, or instead of RE, we might use GM. All right. Now, analogously, we design this with the MOS. The gate is grounded. The input is applied to the source over this internal resistance of the signal. The output is from drain. The output resistance is, of course, the drain resistance if early voltage effects are neglected. And again, using a T analogous small signal equivalent, the input resistance, the resistance looking into the amplifier, is basically this baby, 1 over GM. Why? Well, because between the source and the ground, that's the only resistance. Or we can think of it that way. Input resistance is defined as the input voltage divided by the input current. Input voltage is minus I, 1 over GM, times 1 over GM. And divide this by the input current. The input current should go actually that way. So minus I divided by minus I takes care of that one. 1 over GM appears as the input resistance. And then again, output resistance is RD. Okay. What is the signal dividing role of Rin and Rsig? Since that signal is applied between here and there, so it's basically Rin divided by Rin plus Rsig, and Rin is 1 over GM, so it's 1 over GM divided by 1 over GM plus Rsig. All right. What is the gain? Well, obviously, the voltage over here, the output voltage, is minus I RD, right? The input voltage is the voltage over here, and that's minus I 1 over GM. Divide them. The gain is GM RD. Or you could think of it that way. If you put a load resistance here, it would be RD in parallel to that load resistance multiplied by GM. Or if you think in terms of BJT minus RC divided by RC parallel to RL divided by RE. And that basically is pretty much the same formula. So the gain, the total overall gain, is represented by this formula. Now we remember BJT differential amplifier. We know the common mode gain, differential mode gain, the common mode rejection ratio. Let's do a similar analysis for MOS differential amplifier. Again, we have two identical NMOS. And the input is applied, differential input is applied to the gates. The output is from the drains. So the differential input is the difference between these two inputs, VG1 and VG2. So instead of using two different ones, we can basically use one source. And the small signal analysis yields this circuit. So again, two dependent current sources, GM VID divided by 2 at two different directions. And the other end of the drain resistance is connected to ground, of course. So what is the input voltage? Input voltage on one side is basically the current multiplied by this resistance. The output voltage is the current multiplied by that resistance. So on one side, it's minus GMRD, VID divided by 2. On the other side, it's plus GMRD, VID divided by 2. Okay, what is the VGSs? Because the dependent sources are a function of VGS. It's basically VID divided by 2 and minus VID divided by 2. Okay, so the differential gain is obviously the difference between these two outputs. So it's GMRD. What if we use a current mirror to bias this differential amplifier? The circuit can be pretty much summarized like this. This is what? Question. The inputs are the common mode voltage plus differential voltage, common mode voltage minus differential voltage. So the differential gain is then a function of a few things. First, since these two are identical, they're GMs or GM1, but also this is PMOS, right? So if we cannot neglect the effects of the early voltage, it should have an output resistance. And that output resistance will be in parallel to the output resistance of this first MOS. And so that appears as the drain resistance, right? By using a MOS itself, we created a resistance connected to the drain of this MOS. When we come to the common mode gain, well, the common mode gain, of course, like in BJT, if there is any resistance connected to the common sources, will be a function of it. Because that resistance, if that is not infinite, will create a common mode gain. So that will be GM1, RO1 in parallel to ROT3 divided by 2 RSS. Why 2 RSS? Because the currents sum up here and flow over that if there is a resistance, over that resistance. So the common mode rejection ratio is a function of that resistance and the GM of the first MOS. Now, this way we pretty much come to the end of today's class. There is a course evaluation form on VETI, and I think I also put this onto the messages. I will really appreciate any feedback, whether it's positive or negative. And the feedback, I won't get it until you get your letter grades. All right. And that's so much for today. There are only 3 students left. Berk, are you there?
Yes, I am here hocam.
Okay, buyur. Sahne senin.
Hemen ekran paylaşıyorum. Sanırım görüyorsunuz hocam.
Evet, evet.
Tamam. Okay. Let me have laser pointer. Okay. Hello everyone. Today it will be quite bit long and detailed problem session. We are going to solve different types of questions. It includes DC and AC analysis of different MOS amplifier topologies and differential pairs and logic circuits as well. This is the first question. We are going to analyze common source amplifier topology. We are going to compute voltage gain of this circuit if lambda is 0. If lambda is 0, means that early voltage is infinite, then output resistance of the transistors are infinite as well. As you can see, this is a common source stage. It's obvious because input is applied to gate and output is sensed at drain, right? However, as you can see, there is no resistor connected to source terminal of M1, but we call it this topology, common source topology with source degeneration. Why it's called source degeneration? Because there is no resistor here. Instead of source resistance, diode connected MOSFET M2 is used. This is diode connected because gate and drain are connected together, and it behaves as a resistor in small signal model. We need to build in small signal model of this circuit as shown in here, and arrow is infinite. That's why arrows are not included in small signal model. We need to look into source of M2 here. Let's call it RS. What is the equivalent impedance of RS, like here? RS is actually equals to the voltage difference between this node from this node to ground divided by the current. And gate voltage of M2 is 0. Then in small signal model is grounded as well. Then RS equals to Vs divided by GM2 times Vs minus Vg2. Vg2 is 0. The current value is GM2 times Vs here. Vs is cancelled out from the numerator and denominator. Then RS value, equivalent RS value equals to 1 over GM2. Then we can show this equivalent resistor like that. This is just only resistor in small signal model. Okay. Now we are going to, our goal is to find a voltage gain here. We need to find V out expression. What is the V out in small signal model? It's basically equals to RD times minus GM1 times V in minus Vs. Then what is Vs here? Vs can be expressed as 1 over GM2 multiplied by GM1 times V in minus Vs here. Now let's take the parentheses of Vs in the equation here. Then Vs is calculated, or Vs can be expressed as GM1 divided by GM1 plus GM2 times V. Now we are going to plug this Vs expression into V out equation here. What is the V out? Minus GM1 RD times V in minus Vs. And we derive the Vs expression here. Just plug it here like that. Then we are going to get V out divided by V in equals to minus GM1 RD times GM2 divided by GM1 plus GM2. You can just divide by numerator and then denominator by GM1 times GM2. We are going to get minus RD divided by 1 over GM1 plus 1 over GM2. This is the voltage gain expression for this circuit. Okay, in the question, we don't have numerical value of any parameters. Then voltage gain is expressed in terms of MOSFET parameters. Okay. What happens if a lambda 2 or a lambda of M2 transistor is not equal to 0? Lambda is not 0. It means that early voltage is not infinite then output resistance is not infinite as well. Therefore, RO2 must be included to small signal model like that. Now, what is the equivalent RS for that case? RS equals to 1 over GM2 parallel to RO2. We can write it like that, then it's RO2 divided by GM2 times RO2 plus 1. Again, we need to derive V out expression to find voltage gain expression. This is the V out expression, this is the Vs, okay? Then Vs is equals to GM1 Rs divided by 1 plus GM1 Rs times V in. We are doing same things for the previous case, like just plug Vs into V out expression here. Then we are going to get V out divided by V in equals to minus GM1 RD divided by 1 plus GM1 RS. We know the Rx expression, this is it, like just plug this expression into the gain expression here. We are going to obtain this little bit complex expression. Okay, this is the effect of RO2 in the gain expression for this circuit. Any questions so far? This is a little bit complex, but you need to solve these problems by yourself. And we are going to calculate, or we are going to derive output resistance expression for the circuit. Let's call it R out here, but RD will come to parallel to this R prime out here. Firstly, we are going to find R prime out expression. Okay, R prime. What is the R prime out? It's basically V out divided by I prime out here. Okay, we are going to write this like that, and we are going to follow this path, RO and RS. Okay, what is the current passing through this small signal RO resistance? It equals, this is the total current I prime out minus this current value, GM1 V in minus Vs. Don't forget that in order to find output resistance, you have to kill input voltage. You have to set the input voltage is 0. V in is 0, then current value becomes GM1 times minus Vs. Okay, here we are going to plug into the V out equation. Like, what is the voltage potential difference across the RO? It equals to RO multiplied by I prime out minus GM1 minus Vs plus Vs. Okay, what is the Vs? Vs is actually Rs multiplied by I prime out, because the total current passing through this equivalent resistor, then Vs potential equals to Rs times I prime out. Then just plug Vs into the V out expression here. Then take the I prime out, take the parentheses of I prime out. V out divided by I prime out equals to RO plus GM1 RO RS plus RS. This is the R prime out value. What is the R out? R out is basically R prime out parallel to RD. And we are going to get this expression for the output resistance of the circuit. Okay. And this is the second question. We are going to analyze different topology. It's called common gate topology. How we understand this topology is a common gate, because input applied to source, then output sensed at the drain. Okay, and we have a microphone having a DC level of 0. It means that input voltage has 0 DC level. Okay, this is the 0 volt at DC. Then drain current is constant and its value is 0.5 milliamp. These are the MOSFET parameters: W over L ratio 50, mu n Cox 100 microamp over V square, threshold voltage 0.5 volt, VDD 1.8 volt. Now we are going to find maximum value of RD, and we are going to maximum voltage gain. Neglection lag modulation. Okay, firstly, we need to ensure that M1 operates in saturation region. What was the saturation requirement? VDS must be greater than or equal to VGS minus VTH. Then VDS means VD minus VS, VGS means VG minus VS, then minus VS are cancelled out from the equation. Actually, the inequality becomes drain voltage rate must be greater than gate voltage minus VTH. VGS value, it's given in the question, it's 0.947 volt. We know that input DC input value is 0. Okay, then gate voltage or VB voltage equals to VGS voltage here. What is the VD? Drain DC drain voltage. It equals to VDD minus drain current times RD. Okay, 1.8 minus 0.5 milliamp times RD. What is the VB or VGS? It's given in the question, minus VTH value. Solving this inequality, it shows that RD value must be less than or equal to 2.71 kilo ohm. Then we can say that maximum value of RD equals to 2.71 kilo ohm. Now we can calculate the maximum voltage gain. Okay, we need to drive a small signal model here. VB is a DC bias signal, then it must be grounded in small signal model. What is the V out expression in small signal model? It's just basically RD times GM times VB minus V in. VB is 0 here. Then current value GM multiplied by minus V in here. V out divided by V in equals to GM RD. This is the voltage gain of the common gate amplifier. What is the GM? How can we find GM? GM expression can be written as square root of 2 mu n Cox W over L ID. Mu n Cox and WL are given in the question. ID value is given in the question as well. Then GM is 2.24 millisiemens. What about, then we can calculate voltage gain expression. V out divided by V in equals to 2.24 millisiemens multiplied by RD, 2 times 71. Then it equals to 6.07 voltage gain. Okay, this is our voltage gain for the common gate amplifier. Let's say that desired gain or is 10. We want to have 10 voltage gain here. What values should be chosen for W over L ratio and VB? This is the gain expression. Then this is the RD value. This is the desired gain value. Then required GM can be calculated as 3.69 millisiemens. We are going to use GM formula. Again, there is only unknown parameter W over L ratio here. W over L calculated as 136.2. What is the VB value? We have drain current, we have technology parameter, design parameter, VTH. Then we can calculate bias voltage by using drain current formula. From that formula, VB equals to 0.77 volt. Okay, this is in order to obtain a gain of 10, and these are the required parameters. Any questions so far? We analyzed common source amplifier, common gate amplifier, and now we move on MOS differential pair. And this is actually, was final question, I guess, for the past years.
Yeah, must be one of those final questions.
Yeah, yes, and actually this is so important question, I guess, to understand the MOS differential pair and studying on the final exam. And this is, you can see MOS differential pair, right? There are we have 4 parts of the question. Firstly, we are going to design a MOS current source. Here, MOS current source, it consists of M3 and M4. And remember that it's actually basically same with BJT counterpart, because it's basically its topology has current mirror structure, right? But don't forget that unlike the BJT, there is no gate current in the MOSFET. Okay, we are going to design current source satisfying ID1 plus ID2 equals to ID3. Then the current value of ID3 equals to 1 milliamp. In B part, we are going to find DC values of both inputs, and we are going to check if all MOSFETs operate in saturation region. In C part, we are going to common mode gain. We are going to neglect channel length modulation here. Then at the last part, we are going to find differential mode gain and CMRR. These are the MOSFET parameters given in the question. Let's start with A part. We are going to design current source generating 1 milliamp. Assume that M3 and M4 are identical transistors. Okay. Kn and VTH are given in the question. M3 and M4, this is the passing through these transistors, the current value is 1 milliamp. We know Kn value is basically actually 1/2 mu n C ox WL. It equals to 0.4 milliamp over V square here. And VGS minus VTN. VTN is given in the question. This is the actually quadratic equation. We have 2 roots for VGS. First one is minus 0.78 volt. We cannot use this value because we assume that all transistors operate in saturation region. However, for this value, VGS is less than threshold value. It means that this MOSFET operates in cutoff region. Then just as this value, we are going to use 2.38 volt for VGS of M3 because this value exceeds threshold voltage value and it operates in saturation region. Let's calculate gate voltage of M3 and M4. We know the VGS value and we know the actual source value here. What is the source value of M3 and M4? It's minus 10 volt. Then what is the gate voltage? Gate voltage equals to actually source voltage plus VGS, right? Then gate voltage equals to minus 7.62 volt. Now you can compute the resistance value R1 here. It's just basically apply Ohm's law, 10 volt minus 7.62 volt divided by 1 milliamp. Okay, then it equals to 17.62 kilo ohm. This is the R1 value, and this is the current source design. Okay. Now we are going to check if all MOSFETs operate in saturation region. M1 and M2 are differential input pairs, and these are the identical transistors. Okay. Then what about VO1 and VO2? At DC level, actually, it's same. VO1 equals to VO2. What is the expression for output voltage? 10 volt minus 6 times ID, drain current. Okay. We know the ID value because we know the value of M3. This is the 1 milliamp, and this is the symmetrical structure. Then M1 current or M2 current equal to 0.5 milliamp. Just plug this value into the equation and output voltage becomes 7 volt here. Then what is the VGS value for input differential pair transistors? Just only unknown variable here, VGS, right? Then VGS calculated, it's two rows for VGS. They are minus 0.32 volt or 1.92 volt. We are going to choose 1.92 volt because they operate in saturation region. Okay, this is our VGS value. For DC level, let's say that the input voltage DC level is 0. Okay, it just we choose it arbitrarily. Then requirement, what is requirement for saturation region? VDS must be greater than VGS minus VT, and VT are short threshold voltage. VD drain voltage 7 volt, source voltage minus 1.92 volt here. And what is the VGS value? VGS value 1.92 minus 0.8 volt. It shows that 8.92 greater than 1.12. It's correct, right? Then it means that M1 and M2 operates in saturation region. What about M3? Is M3 in saturation region? Again, we are going to apply same inequality here. VD drain voltage minus 1.92, source voltage minus 10 here. What is the VGS? We calculated it, it's 2.38. Then 0.8 is the threshold voltage value. It shows that 8.08 greater than 1.58. It's correct. Then M3 operates in saturation region. Okay. Now we are going to find common mode gain here. We assume that early voltage infinite, output resistance infinite, lambda is 0. Okay, this is the formula for the common mode gain for the MOS differential pair here, and RD is 6K here. GM1 and 2 differential input transistors transconductance value. What about RS? RS is actually output resistance of the current source, and it equals to output resistance of M3 here. But we assume that early voltage is infinite. It means that output resistance is infinite as well. If RS is infinite here, common mode gain will be 0. Okay. And as a last part, we are going to find voltage gain and CMRR. Let's define it input differential voltage as VI1 minus VI2 here. And according to the this definition, we can say that in the small signal model, VI1 equals to VID over 2, then VI2 equals to minus VID over 2. And these are the dependent current source values in the small signal model here. But I want to draw your attention to the current direction in a small signal model because it's reverse, right, for these two input differential transistors. It's coming from polarity of VGS actually, because current value is basically equal to GM VGS for the MOSFET values. For M2 transistor, we defined a negative VGS here, which is VID over 2. That's why current direction for M2 is toward upper side. Actually, it's flowing into the drain, looks like, okay? Firstly, we are going to find VO1 expression here. What is the VO1 here? It's basically equals to RD times the dependent current here. It's equals to minus GM VD over 2 times RD. Okay. What is the KD1? KD1 is defined as VO1 divided by input differential voltage. Then VID cancel out from the equation. KD1 equals to minus GM RD divided by 2, it equals to minus 2.68. What about VO2 expression? It equals to, it's flowing into the ground here, VO2 equals to RD times GM times VID over 2, then KD2 equals to 2.68. This is the single-ended voltage gain because output voltage is single-ended. What about differential mode? What if the output voltage is differential signal as well? Let's define it output voltage VO2 minus VO1. We have already defined the input differential voltage. Then differential mode gain equals to KD2 minus KD1, and it equals to 5.36 voltage gain. Okay, this is the differential mode voltage gain. What about CMRR? What is the definition of CMRR? It's equals to differential mode gain divided by common mode gain in the absolute value of it. Differential mode gain 5.36, common mode gain is 0. Then CMRR equals to infinity. Okay. And any questions so far?
No questions, guys? No questions? Okay.
Okay. I'm move on the two-stage MOSFET amplifier. Here we are going to perform DC and AC analysis. These are the MOSFET parameters given in the question. A and B inputs are grounded in DC. Q1, Q2, Q3, Q4, and Q6 and Q7 conducting same current value, which is 200 microamp. We are going to design so that all transistors operate 0.2 volt overdrive voltage. It means that VGS minus VTH equals to 0.2 volt. We are going to find W over L ratio for each MOSFET. In the second part, we are going to find small signal voltage gain, and we are going to assume that early voltage is 5 volt. Let's start with DC analysis. Okay, inputs are grounded and ID value 200 microamp. VOV equals to 0.2 volt. We are going to use just drain current actually. What is the drain current for NMOS transistors? 1 over 2 Km prime times W over L V over square here. It's valid for Q1, Q2, Q7 and Q6. Okay, because these are the NMOS transistors conducts 200 microamp. ID is 200 microamp, Kn prime 400, V overdrive 0.2 volt, and only unknown variable W over L ratio here. And W over L ratio for these transistors goes to 25. We haven't calculated, we haven't found only one NMOS transistors W over L ratio, which is Q5, because Q5 conducts not 200 microamp because 2 times higher current it has, because 200 come from here, other 200 comes from here. Q5 conducts 400 microamp. Okay, the drain current of Q5 is 400 microamp. Other all parameters are same, but drain current is 400 microamp. It means that W over L ratio is the 2 times of other transistors WL. Then W over L ratio of Q5 equals to 50. Okay. We have done with NMOS transistors. What about PMOS transistors W over L ratio? Q3, Q4, and Q6 are the PMOS transistor, and all these transistors conduct 200 microamp. And KP1 is 100 here, V over drive 0.2 volt. Then only unknown variable W over L ratio. From this formula, W over L ratio is calculated as 100. Okay. And we are going to find small signal voltage gain for this two-stage amplifier. Voltage gain basically equals to A1 times A2. A1 is the first stage voltage gain of the amplifier. A2 is the voltage gain of the second stage. What is the first stage gain, A1? It's basically equals to input GM times RO2 parallel to RO4, because VDD is connected to ground in small signal model, and source is the input transistor source is a virtual ground, is connected to ground. Then RO4 and RO2 are parallel, right? Then the first stage gain equals to GM times RO2 parallel to RO4. It equals to GM RO divided by 2, because all RO values are equal with each other. Then RO parallel to RO equals to RO divided by 2. What about second stage gain here? In the second stage gain, input node is here, output node is here. Then expression is minus GM of Q6 times RO6 parallel to RO7. Sorry. Then it equals to minus GM RO divided by 2. We have ID and V overdrive voltage values of transistors, and then calculate the GM by using this formula. 2ID divided by V overdrive, GM values equals to 2 millisiemens. What about output resistance of the transistors? It's basically VA over ID. VA 5 volt, ID 200 microamp, then output resistance equals to 25 kilo ohm. Now we have calculated all parameters needed to find voltage gain. Then VO divided by VID, small signal voltage gain equals to minus 625. Okay. This is the small signal voltage gain of the two-stage MOSFET amplifier. This is the last question we are going to solve today. This is the logic gate circuit, consists of PMOS and NMOS transistors. Assume that all transistors are ideal and VDD is 5 volt, is logic 1, ground is 0 volt and logic 0. A, B, and C are our inputs. Q is output here. In the first part, in first frame, this is the PMOS logic, because we have 2 PMOS and 1 resistor here. For PMOS transistors, if input is 0, PMOS is turned on and it behaves as a short circuit. If input is logic 1, PMOS is turned off and it behaves as an open circuit here. Let's look at this case. If one of A and B inputs is 0, it means that one of these transistors will be short circuit and X not directly connected to VDD. Okay, as you can see, one of the inputs is 0. The output and not X directly equals to 1 here. What about if A and B equal to 1, logic 1? It means that M1 and M2 are open circuit and there will be no current conduction here. Then node X equals to ground, 0 volt here. A is 1, B is 1, then node X equals to 0. As looking at the truth table, this circuit performs NAND gates. Okay. What about second frame, second stage of the circuit? This is the NMOS logic actually. In NMOS logic, if input is 1, NMOS is turned on, it behaves as a short circuit. If input is 0, NMOS is turned off, it behaves as an open circuit. if one of the inputs X and C is 0, it means that no path from VDD to ground and there will be no current connection, then output voltage Q directly connects to VDD because there is no current. There is no current passing through R2. Okay, and these are the combinations for this case. And what about X and C inputs are equal to 1? Then it means that M3 and M4 behave like a short circuit. Then output node connected to the ground here, then output voltage becomes 0. As you can see, this is NAND gate as well, but we built it in NMOS logic, and in the previous part we built it AND gate in PMOS logic here. This is the circuit consists of 2 NAND gates, and the output of first NAND gate is connected to the input of second NAND gate here by X node. Okay, and this is the representation of this circuit. And that's all for the problem session. Okay, any question?
Thank you. Çok teşekkürler.
Rica ederim hocam.
We have only 2 students left, Hasan Fatih and Sana Abu Zaid. Are they here? Hasan Fatih burada. Sonuna kadar da dinledi. Sana Abu Zaid, are you here? Okay, well, I don't know why other students are not here with us today, but slowly, we are coming to the end of the semester, and we basically finished the MOS today. Next week, we are going to go over operational amplifiers, and I wish you all a good week. Today is very sunny and a healthy week, and we'll see you next week. All right?
Görüşmek üzere hocam.
Haydi görüşürüz. Bye bye.